Hi everyone, Chris Vaca here again, theoretical physicist. Today I'd like to work another example of Gauss's law for you involving cylindrical symmetry. So let's go ahead and attack this problem together, and let's talk about the various subtleties that we're going to have to deal with when we deal with different materials in the context of Gauss's law. So here's the problem that I've set up for you that I think will be an excellent example. So what we have here is an inner insulating rod here of a radius r1 that has a uniform charge density rho naught. I've decided in this problem to give this inner insulating rod a total charge of plus q. This inner insulating rod has a vacuum cavity between itself and an outer conducting shell, as I've highlighted here in the bright green yellow. Okay. This outer conducting shell, I've decided to make the problem a little bit more interesting, to give it a total charge of minus 2q. Our concern for this problem is this: what is the electric field for all radii away from the center of the insulating rod? Now, a few points I wanted to go over to make sure that we're all on the same page. First things first, right? Many times we think that just because a material is insulating, right, that doesn't mean that it can't do anything electrically. And that's a common misconception, right? What insulating means for a material means that charges cannot travel freely throughout the material. However, that doesn't mean that the material itself cannot be charged. So it's perfectly acceptable to have something that is charged and insulating. We just have to accept the fact that wherever those charges have been placed upon that material, those charges will remain at their position. So when I say the words, I have an insulating rod right here with a uniform charge density, what is being said is, I have an object here where everywhere throughout the volume of the object, there's an equal amount of charge. Now, this conducting shell, again, conductors behave very differently in the presence of excess charge, right? Once a conductor has reached static equilibrium, i.e. static equilibrium is the state when the charges are no longer moving through the body of the material, then what a conductor will do is drive the charges to the surface of the object in such a manner so that the net electric field within the conductor will be zero. So I have told you that this outer conducting shell, this metal shell if you want to imagine, right, has a total charge of minus 2q. However, I haven't told you where that charge is distributed. Is it distributed on the inner shell? Is it distributed on the outer shell? All we can do to solve this problem is use the material property of a conductor, where we recognize that we must insist that the electric field within this portion of the conductor has to be zero, i.e. the volume of the conductor. However, that does not mean just because that there's no electric field within the volume of the conductor that charges cannot distribute themselves across the surface of the conductor. And indeed, we will see that is the case. That's the way that we can get the electric field to be zero within this object. So let's go ahead and attack this problem, right, using Gauss's law in its integral form, and let's talk about the various subtleties that will be dealt with when solving this problem in the context of this flux integral. So as you recall from your lectures, right, you know the following. You know the integral over the surface of the electric field flux. Apologies, that was a little bit of an awkward statement. Let's correct that, right? The flux integral of the electric field across any enclosed surface, much better, right? We know this is equal to the charge enclosed by that surface divided by epsilon naught. So what we want to do is we want to solve for the electric field in all areas, not only using this mathematical feature, but taking into account the material science that we briefly overviewed, right, with regards to insulators versus conductors for this particular problem. So let's go ahead and identify the various radii of interest for this problem, i.e. the various regimes where we want to know the electric field, right, and talk about what must be happening at the boundaries of those regimes. So if we go ahead and take a look at the premise of our problem here, right, we have a rod here, right, that is insulating, has uniform charge density, and I've told you from the premise of the problem that that rod right there that's charged up, it has a radius of r1, right? So we want to know the electric field within the rod. Furthermore, we have a vacuum cavity here between the rod, right, and the outer conducting shell. This vacuum cavity right here, that's going to be for radii between R1 and R2. I need to know the electric field from R2 to R3. That's the electric field within the cavity of the conductor. That one's kind of easy already. I know E field net in there has to equal 0, right? Again, that's just the property of conductors in static equilibrium, so that's quite nice, right? And then finally, right, I want to solve for the electric field outside of this entire system. Cool. Little other detail in case I forgot, or a quick reminder, right? We're saying that inner insulating rod has a total charge of plus Q. This outer insulating charge, this outer conducting shell, right, has a charge of minus 2Q. So we know this system overall has to have a charge of plus Q plus minus 2Q, or an overall charge of negative Q. And our answer should reflect that when we finish up and calculate. Now, I've told you that these rods, right, insulating rod, and this outer conducting shell have a length L, right? Notice that I've not quite finished my drawing. I'm trying to indicate in my drawing that the length of this configuration is much, much greater than any of the lengths associated over here with the radii of the cross sections of this problem, right? This is going to be very important because it's going to greatly simplify our calculation of that electric field flux integral. And indeed, it'll make the problem tractable because we won't have to deal with these nasty ends where we're going to have these nasty electric fields. So, good thing. So, let's go ahead and attack this problem, and let's talk about the various features that we need. So, first things first. This problem has cylindrical symmetry. So, because this problem has cylindrical symmetry, the natural surface over which we want to calculate the electric field flux would be a cylinder as well. So, in other words, we're going to create a little flux integral here, and we want to integrate the flux of the electric field across this cylindrical surface. Furthermore, my friends, right, what we're going to do is we have to designate a variable that'll keep track of where we're calculating the electric field. I'm going to introduce a fourth radius into the problem. Yes, I know, right? That fourth radius, I'm going to call that lowercase r, okay? Lowercase r stands here for, right? Lowercase r is the radius where I want to know the electric field. So it's really important that you keep track of all these radii, right? We're already at 4 at this problem, right? So knowing the definitions and what they actually physically mean in the problem, super important, right? To make sure that we don't get mucked up, right? And get confused about what the meaning of the various radii are. So sometimes I find when I'm doing problems like this, it's nice to have like a little table over here or a legend where I designate the various variables, right? So again, the R1, R2, R3, right? These are related to the problem, right? In terms of the geometric description of the charge distributions. So these are material radii. And then little r, right? This is a mathematical radius, right? This is where I want to actually know the field, right? So radius of interest. Remember, do what works for you, right? There are many different paths to get to the right answer, right? I'm just giving you hints and tricks, right, that I've learned throughout my entire career, right? Again, I've done tens of thousands of pages of algebra, right? So it pays to, listen to the words of an old fart like me, okay? All right, so fantastic, right? Let's go ahead and take our little Gaussian surface, right? And let's use this Gaussian surface to calculate the electric field for various radii of interest. So I'm actually going to go a little bit backwards here, but I'm going to take advantage of the fact that I already know all the charge enclosed in this problem. What I'm going to do is I'm going to set up my Gaussian surface integral over here. So I'm going to take my diagram right here. And what I'm going to do is I'm going to solve for the electric field. So this is the electric field strength, right? For positions of interest greater than the maximum material radius, or in other words, that outer edge of the conducting material cylinder, right? So I want to know the electric field for little r's greater than R3. So I'm going to go ahead and create my Gaussian surface, talk about the features of my Gaussian surface, and knock out this calculation very quickly, taking advantage of the work done by Gauss. So again, I create a new cylinder here, yes? But remember, this new cylinder is not real, right? It's a mathematical entity that's used to facilitate our calculation of the electric field strength for this problem. So here, there we go. There's my Gaussian surface right there. Neat. Then I give it a radius here. Little r, right? I remind myself that little r must be greater than r3, where r3 was, again, that radius that led to the outer edge of the conducting shell. So I'm going to go ahead and finish off my cylinder here, right? I'm going to pretend that I went off to that distance L very, very far away. And so let's go ahead and take a look at our flux integral here, right? So got to calculate the flux of the electric field across 3 surfaces, right? But in fact, this ends up being 3 geometrical entities. And again, apologies for my terrible 3D diagram, right? The 3 geometrical entities over which I want to calculate the electric field flux are the following. So let's go ahead and label those surfaces. We'll call this surface in the front surface number 1. We'll call this surface in the back surface number 2. And we'll call this surface in the middle surface number 3. And I got to fix my geometry here. This is making me very upset. So ugly. I think that's much better, right? So take a look, right? Surface number 1, this is one of the end caps of my mathematical cylinder for my flux integral. Surface number 2, again, the other end cap of my mathematical cylinder. And surface number 3, that's this circular cross-section, right? All around the edges over here. So let's go ahead and take a Gandarino here, right? And separate our flux integral into the 3 pieces. In addition to this, remember, standard convention is we do what with flux integrals, right? In Gauss's law, well, remember, we take the Western convention where we pick the unit normal to be pointing out of the volume enclosed by the surface, right? So remember, technically, surface number 1 has a unit normal over here, N1, right? Surface number 2 has a unit normal, N2. And then surface number 3, it has a unit normal, N3, which again would be pointing all around in a circle like this. Let me see if I get my fingers just right. Yes, around that outer edge away from the volume enclosed. Okay, so let's go ahead and calculate these 3 flux integrals. E dot dA1, E dot dA2, and then finally we have E dot dA3. So remember, there's no such thing as an infinite object in the universe as far as we know, right? So we want to make sure that we're understanding our calculation here, and we want to really make sure that we capture the most important element of this flux integral. So remember, I did tell you something though, right? That was going to make this flux integral a little bit easier to do. The thing that I told you is we're going to make the assumption that both this insulating rod on the inside and this outer conducting shell are very, very long in comparison to their cross-sectional geometric parameters of description, right? Or in other words, that the length of this rod and the length of this conducting shell, right, is much, much greater than the radii of their cross-sections, okay? Now, what does that do for our flux integral? Well, despite the drawing that I've done, right? Remember, I'm assuming that this outer edge is very, 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 very long, right? And if that outer edge is very, very long, it's telling you something very important about the ratios of the surface areas of cap 1, cap 2, versus the area of the outer cylindrical section, right? And what it's telling you is area 1 and area 2 are very small in comparison to this area right here on this edge of the soda can, as we can see, okay? As such, right, we can make the following approximation. The following approximation we can make is we can approximate both of these integrals to be 0. Now, we're not actually saying that the integrals are 0. Rather, what we're saying is that these integrals right here, in comparison to this one, are negligible, right? And really, because this is the biggest area, right? That huge old area right there, right? That's going to create the greatest contribution to the flux integral of the electric field for these cylindrically symmetric charge distributions, right? On both our inner insulating rod and our outer conducting shell. So we're going to take this part right here as the only part that will create a significant contribution. you may bring up an excellent point, right? The excellent point you're going to bring up is, well, these are finite rods, right? This is a finite conducting cylinder. Very obviously, they will have an electric field at this end cap. And you're right, absolutely, right? It will be a finite electric field for real charge distributions, right? And that will create flux contributions here at the end. But nevertheless, even though that the electric field term is not zero, right? The fact of the matter is, when we add up all these contributions for every single little area tile that we put down here at the end cap of our cylinder, well, we know that that area cannot possibly make up for the strength of the electric field at the ends, right? Versus the geometric difference between the size of this area versus these two end caps. Don't let my drawing fool you, right? Obviously, on my drawing, end cap 1, end cap 2, and this outer edge of the soda can, right? Their areas are comparable. But again, I told you that the premise of the problem is that that outer edge of the soda can is super freaking long. And I think it's obvious that that outer edge will have the greatest area. So you're just like, but wait, right? Maybe there's something else here, right? Because you're telling me the area is small, right? And you see that and you agree with that, right? But then you say, but maybe I could make up for it using the electric field strength. And that is an excellent argument too, right? After all, it could just be that at the end caps, the field's super strong, right? And then on this outer edge, that the field is quite weak, right? So that would mean that our negation of these terms, right, may be misfounded, right? Or maybe we're doing something silly here, right? But I say to you this, right, that in a reasonable sense, right, if I were to pick a little r here, right, such that little r was about the same distance as these end caps were to the charge distributions on the conducting cylinder or the insulating rod, I make the argument that, oh, well, I could construct a Gaussian sort of like soda can here, right? A Gaussian little cylinder of surface, right? Such that the distance to the end caps is approximately same to the distance to the surface of the conducting cylinder here. And in that case, we can make the argument that the E field strength should be roughly comparable on those areas. So really, once again, the only thing we need to compare is the areas themselves to decide which are the most important contributions to the flux integral. Cool. So I think I've justified enough why we can throw away the end caps. Let's go ahead and move on. So let's take a look here. We really need to only do integral number 3 to get the total flux integral. So we said the flux integral of the electric field out of this Gaussian soda can surface, right? Well, the major contribution to that comes from this outer edge surface. Furthermore, right, we're going to assume, right, again, by virtue of assuming that the soda can, right, the cylinder is incredibly long, is we're going to assume that the electric field strength on this outer edge right here, that E field strength is effectively uniform. And that seems pretty reasonable, right? You would imagine that if I'm in this sort of inner vicinity, right, of my conducting cylinder, right, that I'm not going to see significant deviations in the strength of the field nor in its direction, right? It's only really at the end caps where we're going to start to see large changes to both the geometry and strength of the field, right? And since we already assume that my cylinder here is super duper long, then we know for the most part that it's a pretty good approximation to treat the electric field as being constant in strength on this outer edge of the soda can. As such, because we have this cylindrical symmetry, we can say the following. Oh, well, my unit normal points out. Furthermore, right, I know that my electric field, right, has to either point radially out or in from this given surface. So this flux integral can be greatly simplified. We can write this as the integral over surface number 3, that outer curved surface edge. We can write this as magnitude E at that little radius r, right, times dA times cosine of 0 degrees, because we're assuming that the field and the unit normal to the area, which again would be this little n3 vector that would go all around the edge of the soda can, right, we're going to assume that those are always collinear on that surface, right? And so as such, right, we get the following. We get that the electric field strength is constant across the surface, so then we have to add up all these little dA tiles everywhere all along surface number 3. Bada bing, bada boom. And we add those all up. So how do I calculate the area of that outer surface of a cylinder. Well, again, let's go ahead and draw a little quick cylinder right here, 90 degrees in comparison to our picture. So I got a little radius right here, a little r, right? And so I want to calculate this area right here, this outer soda can edge, and that area right there, given that the cylinder is L long, that green area, well, that is equal to L times 2 pi r. All good? And apologies, covering my answer up with my face, right? And again, no one wants to see that. So got that nice little green area. Makes sense, right? What I did is I calculated the perimeter of a circle, right? And given that the cylinder is L long, right? Again, just multiply those two to get that outer edge surface area. So important note here, right, that we need to talk about with our calculation, because we are making assumptions about the electric field in this flux integral, which may not actually be true in this problem, right? The assumption we made was if the electric field points out, right? That has to be our answer, right? But we could also get another version of this answer, right? Because the other version of the answer could be, well, we assumed the E field was pointing out, but what if it was a negative rod instead, right? Indeed, right? We already said from the premise of our problem, right? Oh, this outer shell has a charge of minus 2q, right? In this inner insulating rod, right? This only has a charge of positive q. So in fact, the net overall charge enclosed over here, right? We see that, oh, well, it actually isn't positive, it's negative. So we wouldn't expect field lines to be leaving the surface of this conducting cylinder in this inner insulating rod. We would actually field lines, instead of going out, we would expect them to be coming in. So we go ahead and take a look at our flux integral, right? And we see, oh, well, if we expect them to go in, we got a little bit ambitious here, right? Because it's not that the angle, right, between the E field and the unit normal to the surface is 0. It could be that if we're surrounding overall negative charge, right? Well, if we're surrounding overall negative charge, right, then that angle between the field and the unit normal, well, that's not 0. That's 180 degrees, right? So when you're doing these sort of problems in Gauss's law, it pays dividends, right, to think ahead as to what the answer should be. And that's a little frustrating. I understand, right? You're just like, after all, well, if I'm calculating the thing, why should I already know the answer? And you're absolutely right. You shouldn't know the mathematical form of the answer, right? But we remember the words of great physicists from the past, right? Don't calculate the answer to something you don't already know the answer to. And you're just like, what the hell does that mean, right? What I mean by that is you should at least have some intuition as to what your answer should look like. In real physics, right, many times the way you get that intuition is you have a set of experimental data, right, and you're trying to get your theory, right, to make predictions of that experimental data, right? But when you're doing sort of like these introductory physics problems, again, you have a pretty good notion of what things should look like. And so since the charge configuration is overall negative, right, we should have been a little bit more careful here, and we should have recognized that in our flux integral that the field wasn't pointing out, but rather that the field was pointing in. So the dot product between the electric field and the area tile for Gauss's law here shouldn't be a 0-degree angle between the two, but rather 180. So we need to slap a nice little minus sign right there to take that into account. After all, right, we want to make sure that when we calculate electric field strengths that we get our answer to be positive, which, my friends, would then require us to be very careful about this unit normal issue, right, with regards to our charge distribution. So indeed, for this problem, we suspect that the field's going in, so we put a 180 degree there, and if we're correct, then when we calculate the strength of the field, right, then we should see that the strength of the field should come out positive. And I'll tell you later what's the worst that could possibly happen if you didn't take this into account. You're going to get a little bit of a silly answer, but the answer itself will tell you that, hey, indeed, you missed a little detail here with that unit normal, but it's okay. But again, wanted to make sure that we correct that before we proceed on. All right, fantastic. So now I got this little flux integral Reno, and so I get negative magnitude of the field at that radius r of interest times L times 2 pi r. What we get right here is this is equal to the charge enclosed by my cylinder divided by epsilon naught. But that's an easy charge enclosed, right? It's just the charge of the outer conducting shell, right? Plus the charge of the inner insulating rod, minus 2q plus q, boom, minus q overall. And so indeed, we get a minus q, right, over epsilon naught right here. All good. So then we have all that. Fantastic. Then we can make that equal my electric field strength magnitude with the minus sign in front times an L over a 2 pi r. Hunky-dory, funky fresh. Again, let's do a little bit of algebra right here. Let me switch the colors. Make the algebra a little bit easier to follow. Minus signs cancel. Cool. And so I get the electric field strength at the outer surface is as follows. I get that this is equal to Q over 2 pi epsilon naught L R. Let me rewrite this in a little bit more familiar of a fashion. Q over L, we recognize that as coulombs per meter, right? Or that has to be a lambda. So we get the field strength is just equal to lambda over 2 pi epsilon naught R. And our hearts pitter-patter with joy, right? Why do our hearts pitter-patter with joy? Because this matches the answer of a long straight rod. And what's really neat about that answer is that we can't tell what's going on the inside of this charge distribution if we're really, really far away. So if we were really far away, we wouldn't see the structure of the nested conducting shell and the inner insulating rod, right? What we would see is just a little tiny strip of charge with the charge overall of minus Q, right? So since we already know the electric field strength for an infinite rod, we knew our answer here, right, had to match that, and indeed it did. So let me go back to that original problem where we were talking about that unit normal, right? And you're just like, well, what if I didn't know this, right? What if I assumed the field was pointing out instead of in, right? Well, what you would have noticed in your answer at the end of the day, you would have seen a minus sign here in your answer. And so that would have told you immediately that you got the unit normal wrong, right? But that's all right, right? Because if you got the unit normal wrong, then you would just go back to your flux integral calculation, indeed correct that angle between the field, right, and the unit normal for the little area tiles that are used in Gauss's law. So indeed, if you got a minus sign, you know that you had to goof somewhere in the directions, because remember, magnitudes have to be what? Magnitudes have to be positive definite, right? So if you got a minus sign equals a magnitude, then you know that your unit normal calculation and your electric field calculation, right, up there, right, you need a little bit of a modification. But since we got a positive magnitude, as we expected, we know the following. We know the electric field for radii, right, that are greater than the outer radius of the outer conducting shell. We know this is equal to minus lambda over 2 pi epsilon naught r hat, where r hat is a unit normal vector that points radially away from the central axis of our problem here, right? R hat, unit vector, away from central axis. Beautiful, right? And this is our electric field when little r is greater than R3. Gorgeous. Now, let's keep on going and let's attack the rest of the problem. Well, I already told you I knew the answer in a particular area, right? I told you that I knew the answer of the electric field, right, for the following radius range. So if I go back to my original drawing, right, what I see is R2 and R3 right here. If I'm in a little radius R in between these two, right, I'm in the cavity of the conductor, right? And you know that there can't be electric fields in conductors in static equilibrium. So we already know the answer for the electric field right here. The electric field strength right here, this has to just equal 0. Cool. But let's go ahead and quickly draw a diagram and let's look at the implications of this calculation. So there's no way you could have known that answer unless you knew this property of conductors, right? There's no math formula, right? This is just a feature of a material, right? And as such, right, we need to insert it into our answer in that empirical sense. But if I go ahead and quickly redraw my drawing, the fact that we know electric fields have to be zero inside of conductors in static equilibrium, well, that tells us quite a bit about how this charge is behaving on this outer conducting shell. Let's go ahead and talk about it, right? So I told you this inner rod has a charge of plus Q, yes? And then I told you this outer conducting shell, right? It has a charge of minus 2Q. But I didn't tell you where that charge of minus 2Q was other than it was at the surface. And the fact that we need the electric field inside of this conducting material to have net electric field of zero tells us how that charge is distributed across the surface. Let's go ahead and think about this, right? So I have minus 2Q overall on this thing, yes? But where is that minus 2Q on the surfaces? And I make the argument that that minus 2Q has to have distribution on the inner surface of the following and outer surface of the following. I say that this outer surface right here has to have a charge of minus Q, and then I say the inner surface also has to have minus Q. And if I add the charges on both of those surfaces, then I get the minus 2Q charge overall of the conducting shell. And what's the argument there? Well, again, if I was to create my little Gaussian surface right here, right, of radius r, I know that the integral of the electric field on this little Gaussian Coke can, this little Gaussian soda can here, right? I know that E dot dA on this surface immediately is equal to 0, right? Again, this is just the property of conductors in static equilibrium. But then that means that Q enclosed over epsilon naught also has to equal 0, right? And since permittivity can never be equal to 0, right? After all, it's just a constant of the universe, right? The only conclusion I can draw is that Q enclosed has to equal 0. And so that's a big hint, right? Because you take a look, well, I know I'm enclosing the plus Q of the inner insulating rod, right? So then that means somewhere, right, on this conductor, there has to be a minus Q worth, right, as well to cancel off the plus Q of the inner insulating shell. Excuse me, not the inner insulating shell, the inner insulating rod. But final piece of the puzzle is, I told you conductors can only carry that charge on the surfaces in static equilibrium. So the only conclusion I can draw is bada bing, bada boom, plus Q has to be minus Q on this inner surface. Furthermore, we also really love this answer for the following reason, right? We love this answer because if I'm at little radii r, right, greater than r3, right, you see, oh, well, this inner insulating rod and this inner radius surface of the conducting shell have net charge of 0 overall. It tells us that all the excess leftover charge of the outer conducting shell has to be distributed on this outer surface right here. And indeed, it has to give us the electric field of a rod, right, that is negatively charged on its surface, right? So another nice little feature right there. So boom, we already know the electric field within the inner cavity, and it gave us information about the charge distribution, right, on the surfaces of the conducting shell. So now let's go a little further here, right? And let's do the electric field for little radii greater than the radius of the inner insulating rod, but less than the inner surface of the conducting shell. Well, this one isn't too bad. We go ahead and do our flux integral again, but our flux integral, its unit normal, is going to be a little different from beginning. We'll go ahead and talk about that right now. Again, we're going to ignore those end caps. We're just going to move on, right? We've already had that discussion. The same things apply here. And so I make the argument that this flux integral just has to be the following. Strength of the field at that little radius r right there, right, times length of the shell times 2 pi r. And I say this has to be greater than 0. Why do I say that this has to be greater than 0? Well, it has to be greater than 0 because remember, I'm making a Gaussian surface here, right, in this vacuum cavity, right? And in this vacuum cavity, you notice that the charge enclosed is only positive, right? And that's really important because remember for electric fields, for positive charges, right, that they have to point away from the positive charge. So indeed, over here, we shouldn't expect any tomfoolery with the unit normal, right, on that cylindrical surface. So we can assume the flux integral is going to come out to be a positive number 2. In fact, we know exactly what that number has to be. It has to equal Q enclosed divided by epsilon naught, but we already know what the Q enclosed is at this Gaussian surface that we're describing here, right? Where I'm integrating in this cavity right here, right? I know I'm only surrounding the positive charge of the insulating rod right there. And so indeed, my friends, I know that this is just equal to plus Q divided by epsilon naught. And so if we go ahead and take all our pieces together, so we take E R times L times 2 pi R, this is equal to plus Q over epsilon naught. And indeed, my friends, we get the expected result. We get that this just looks like a thin rod, right, at this distance little r away from its central axis, right, as it had to be, right? In this vacuum cavity, right, I can't tell what's happening on the inside of this insulating rod, so it just has to give me the electric field of a charged infinite rod a distance r away from its central point, right, perpendicular to the long axis here. Cool. Or indeed, if I want to write this in vectorial form, electric field at this little distance r, this is plus lambda over 2 pi epsilon r, little r hat, right, for little radius between r1 and r2. Boom, boom. Know the electric field there. Know the electric field here. Know the electric field there. Only one other place to calculate the electric field strength. Last place to calculate the electric field strength would be in that final part of the charge distribution volume, aka I want to calculate the electric field strength, right, within the radius of the insulating rod. So let's do that, right? We want E field of little r for little r less than r1. Again, let's go ahead and draw a picture here. Boom, boom. Boom, boom. Boom, boom. All right. Again, here's our outer conducting shell. Right, here's our inner insulating rod. Here's our radius, R1. And I want to calculate the electric field for a little r that's within this volume of this insulating rod that has a total charge of plus Q. So, same deal as before. Let's do that flux integral real fast. We'll ignore the end caps yet again. E that dA on that little soda can, we know that's just going to be electric field strength at that location of interest, right? Times L times 2 pi R, get that outer edge area of the soda can. Furthermore, since we're only surrounding positive charge, we can assume the field that field is pointing radially away from the central axis of the insulating rod. Fantastic. So again, no tomfoolery with the unit normal and the electric field direction, right? And their dot product. Okay, so we got that once again, and that has to equal to Q enclosed over epsilon naught. Now, Q enclosed here is a little bit different, right? It's not as nice as our previous calculations, right? Because now we're not surrounding all of the charge of the insulating rod in the center. We're only surrounding a portion of the rod. And it's going to be similar to these proportionality arguments that we made in a previous video, right? When we were calculating electric field strengths due to linear charge distributions. The argument goes as follows. Q enclosed divided by the total charge has to equal the volume enclosed at little r divided by the total volume of the insulating rod. The argument is if the volume that we are surrounding with our Gaussian surface, right, constitutes 1/2 of the total volume total volume of the insulating rod, it should also contain half of the total charge, right? So let's go ahead and calculate that enclosed volume. That enclosed volume, that has to be L times pi r square. Makes sense, right? Cross section of a circle, right, times length of the cylinder, right? This has to be the volume enclosed. But the total volume of the rod has to be L times pi r1 square. Makes sense, right? Again, total insulating rod has a outer radius of r1 right there, right? So this has to be its total volume. Good. So then we can get the charge enclosed here plus Q. Let's go ahead and cancel off the relevant prefactors and everything, right? So boom, L, boom, go away, pi goes away, good to go there. And so we get Q enclosed has to be plus capital Q R square over R1 quantity square. Indeed, seems like a reasonable answer. We'll check it at the end by insisting upon continuity of the electric field at the edge. Okay. All right, beautiful. So now we know everything that we need to know to calculate the electric field strength within the volume of the insulating rod. What we get here is ER strength times L times 2 pi r, that this is equal to 1 over epsilon naught plus Q little r square over capital R1 square right there. All right, let's go ahead and deal with the wreckage now, right? So we go ahead and move relevant terms. So then we get ER here. Cool, cool, cool. Then what we get here is as follows. We get a lambda. Remember, plus Q over capital L. We call that lambda. And then we get a 2 pi epsilon naught right here. And then what we get here is an R over an R1 square. How did I get that? Well, remember, this power of R right here gets rid of one of these powers over here. All the other prefactors came along, and then this is a constant that came from the charge proportionality argument. So, again, looks a little funky, but the units work out. Indeed, you see that you got meters up here and meters square right here. So you get a 1 over meters right here, as we expected for the electric field strength, right? Good to go. Magnitude came out positive. We're happy about that too. So indeed, this does have the correct units for an electric field. Furthermore, since we're surrounding positive charge, we know what the electric field strength has to be at this little radius. This has to equal lambda over 2 pi epsilon naught capital R1 square times little r in the numerator. And this is all pointing radially out, and this is for little r less than R1. So I told you, there's one last little check you can do to see whether this electric field strength makes sense or not. And that last little check is E fields should be continuous across physical boundaries that do not have infinitesimally thin charge distributions. So let's go ahead and talk about this. So if we go back to our top problem right here, again, the original premise of the problem, what I'm saying is this, right? Since there isn't an infinitesimally thin boundary of charge right here, whatever the electric field strength is at this boundary as predicted by our calculation on the inner radii at this boundary versus the outer radii at this boundary, mathematically speaking, the electric field strength should be a continuous function at that boundary. You may say, oh, okay, so should it be continuous at this surface here? And the answer is no, it shouldn't be continuous because we have made an important mathematical distinction between the nature of the charge distribution across this boundary versus the charge distribution across this boundary. At this boundary, the charge distribution is finite, it's not infinitesimally thin, so field strength continuous. But here, because the charge is only distributed upon the surface, and we've made the mathematical approximation that the charge is distributed on a really thin, in fact, infinitesimally thin layer, right? Well, then here, right, an additional rule has to be applied, right, in order to calculate the electric field strength across the boundary, right? Again, several introductory textbooks have this rule, right? The rule is that when you go across a charge distribution that's infinitesimally thin, right, that the electric field should change by a factor of the charge density per unit area divided by epsilon naught. But just know continuity only applies at boundaries where you don't have thin, and I mean thin in the most extreme sense, infinitesimally thin layers of charge. So I go back to my electric field down here, and indeed, right, we see right there the following result, that here's my electric field for radii of interest that are less than that outer material radius of our inner rod, right? Notice that electric field formula, if I was to plug in little r1 right here into the electric field in the vacuum cavity, I would get lambda over 2 pi epsilon naught r1. If I were to plug in r1 to the electric field calculated within the cavity of the insulating rod, again, once again you see that electric field matches at the boundaries, right? So I hope this video has helped you to understand how to apply Gauss's law for cylindrically symmetric charge distributions in the context of both conducting materials and insulating materials as well. But let me know if you have any additional questions or concerns in the comments section of this video. Otherwise, I wish you the best of luck, right, in doing future calculations involving Gauss's law, and keep it hunky-dory, funky fresh, or as the kids say, hudfa, and have a wonderful day.